For this lesson, we're going back to the simulator and getting ourselves some more samples. This simulator is set up to support a 2-sample t-test. For this case, since we're doing a 1-sample, we'll just be ignoring this column. Let me set a mean here and hit return and draw my 7 samples out of this universe. What we're trying to do with a 1-sample t-test is see what we can discern about the mean of the population given this set of samples. So I'll copy this and we'll paste that into QuikSigma. From the toolbox, I've selected the t-test, and within the t-test I've selected a 1-sample t-test. Normally when we do this test, we don't have the luxury of knowing the mean or standard deviation of the population from which the data were drawn. But in this case we do, so that's handy. Let's just put 150 in there, which we know is the population mean, and see what QuikSigma tells us. Okay, this is a very predictable result if you think about it. It says, as far as I can tell, I cannot tell you that the mean is less than 150. I cannot tell you that the mean is different from 150. And I can't tell you that the mean is greater than 150. Well, what would you expect? In fact, we get these confidence intervals. The middle one's particularly easy to understand. What that says is if I kept on drawing samples of 7 out of this population and did that many, many times, 95% of the sample means would fall between 139.8 and 167.2. All right, let's try to tie this to a practical example. Let's say we've got a process that's running and the target is 170. Now we don't want to over-adjust our process. We don't want to respond to normal random variation, but we'd like to know if really our process has drifted. And we can get that here by clicking Calculate. And probably the first thing we would pay attention to would be the middle hypothesis. That is, there's only about a 2.5% probability of being wrong if you assert that the population mean is now different from 170. So, yeah, it's time to readjust the machine. Now, just for thoroughness, let's get in the habit of checking assumptions. The data are normally distributed as far as we can tell, and as far as we can tell, they're stable and predictable during the sampling interval. So, yep, we've got a good model. The decision to readjust the machine under these circumstances will almost always be correct.